Hello, good afternoon, dear students. Yes. So, in our previous session, we have studied about the colligative properties. Okay, so we have studied two important colligative properties, right? So, what do you mean by colligative properties? What do you mean by colligative properties? Yes. So, colligative properties. Yes, so these properties, it is a property of the solutions, okay, where it depends only on the number of solute particles and not on the nature of the solute, okay. Such properties, they are called as the colligative properties. Yes, good afternoon. Okay. So we will start now. Okay. So we have seen there are four important colligative properties, that is relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. Okay. So lowering of vapor pressure, we have discussed this as a case. Okay. We have discussed this as a case, and also in the previous session, we have seen the formula to calculate the relative lowering of vapor pressure. So here there will be a non-volatile solute, and non-volatile solute is added in a volatile solvent. Okay. So how it is relating? Okay, how the vapor pressure? Okay, how it will be related and how it results into the lower vapor pressure. So that we have seen, and this is a formula calculating the relative lowering pressure. So we have seen this all things. Okay. So how do you calculate the number of moles? So you know number of moles can be calculated by given weight upon the molecular mass, right? So mole fraction also you know. So if you want to calculate a mole fraction of a particular component, so the number of moles of a component, that component to the total number of components in the solution. Okay, so that is the mole fraction. So by this, we have seen what is relative lowering pressure. Next, we have also seen the elevation in boiling point. Elevation of boiling point, yes, it is the temperature at which its vapor pressure becomes equal to atmospheric pressure. Okay, so we have seen the formula to calculate the elevation in boiling point also. So you might have noted it down in the previous session, right? So please make a note of this again. So we have seen how to okay, get the elevation in boiling point. So this is the formula, that is MB. Okay, MB is equal to 1000 into KB into WB divided by delta TB into WA. So this is the elevation in boiling point. So by this formula, we can calculate. So WP is nothing but it is the weight of the solute, okay, in molar mass. Then your molar mass is MB. So we have to calculate the molar mass of the solute, okay. So how we can calculate the molar weight of the molar mass of the solute is 1000 into Kb. What do you mean by Kb? Yes, Kb is the molar elevation constant. WB, it is the weight of the solute. Okay, delta TB, it is the elevation in boiling point. Okay, elevation in boiling point. And WA is what? It is the weight of the solvent. Okay, so like this, we can calculate the molecular mass of the solute can be determined by this formula. Okay, okay, fine. So please note this formula, very important. By using this formula, we are going to solve the questions, numericals. Then we had to discuss about freezing point. Okay, depression in freezing point. So you can see the graph. Okay, wherein the graph. Okay, you can see the variation. What you can see in the graph, it represents the variation of vapor pressure of a pure solvent and a solution, okay, as a function of temperature. You can see vapor pressure versus temperature. The graph is of vapor pressure versus temperature. So how the variation? So what is pure substance? Pure solvent means it consists of only pure component of solvent, right? So pure component, it consists of only solvent, and solution means there will be both solute as well as solvent. So how it varies, how the vapor pressure varies in a pure solvent and a solution. Okay. So this is the graph where you can see the variations. Okay. So you can see as the liquid is getting freezed, so you can see the how the liquid, yes. So as the liquid is freezing at a temperature, what will happen when the vapor pressure of the liquid solvent will be equal to the vapor pressure of the solid solvent. Okay. So the freezing point. So this is a freezing point of a solution, and this is a freezing point of the water. Water is a pure component. So what will happen? So this particular temperature, okay, here what will happen? The vapor pressure of the liquid solvent will be equal to the vapor pressure of the solid solvent. So from this graph, what you can observe? Yes, from this graph, you can observe that the vapor pressure of the solution is always lower, right? So vapor pressure is always lower of the solution as compared to that of the pure solvent. So vapor pressure, when we are discussing the vapor pressure, okay, you can see vapor pressure is lower here, okay, in case of your solution as compared to the pure solvent. Okay, so as a result, what will happen to freezing point? Freezing point of the solution will be always lower and that of the pure solvent. So you can see the plots, right? So as the vapor pressure of the liquid solvent is equal to that of the solid solvent, okay, that is your solid solvent, what will happen at this point? The graph, you can see that the vapor pressure of the solution is always lower as compared to that of the pure solvent. Okay, so as a result, the freezing point of solution will be lower as compared to that of pure solvent. Solvent taken is your water. Okay, so how this freezing point, the change in freezing point is taken. So the change in freezing point is taken as delta TF. Okay. So let TF naught. What is TF naught? TF naught is the freezing point of the pure solvent. So let we consider that TF naught is the freezing point of pure solvent and TF be the freezing point of the solution. Okay. So the depression means what? The difference. Okay. So difference in the freezing point, it can be calculated as delta TF. Okay, how it is calculated? As delta TF. So delta TF is equals to T naught of F minus TF. Okay, so this is depression in freezing point. Okay, depression in freezing point. So what do you mean by depression in freezing point? It is a difference. Okay, it is a difference between the freezing point of a solvent and freezing point of the solution, because freezing point of solvent will be more as compared to that of solution. So always the difference is taken from higher minus lower. So which will have a higher freezing point? Your water, that is your solvent. So solvent. So the difference between the freezing point of solvent and freezing point of solution, okay, is your depression in freezing point. Okay, so this is the from the graph. Okay, so what you can see from the graph. So experimentally, so when you conduct this experiment, so it is observed that delta TF, okay, the difference in the freezing point is directly proportional to the molality. Okay, now if you remove this proportionality sign, then you have to introduce a constant, that is Kf. Okay, what is this Kf? So Kf is nothing but your molar freezing point depression constant. So what is Kf? Kf is the molar depression freezing point depression constant. Okay, so this Kf is the freezing point depression constant, or it is also called as molar depression constant. So we are introducing the what your constant. So if you want to calculate the weight of the so by this we have got this particular formula, that is delta TF is equals to KF into M. So this is the formula, okay, for calculating the difference in your freezing point. Okay, now if you want to calculate the what is that weight of the solute. So how it can be calculated? Weight of the solute is nothing but it is dissolved in WA grams of solvent. Then how molality is given as? So you know that how molality is counted, right? How this M is counted. So molality is nothing but amount of solute dissolved in 1 kg of solvent, right? So it is 1000 divided into WB, that is the amount of solute, divided by MB, okay, into WA. So this is the from what is molality. Okay, this is about molality. Now, if you substitute, so here we had got a equation, that is delta TF is equals to KF into M, right? Now, what you do, substitute your this value, okay, whatever you got this value in delta TF. So what I'll get, so delta TF is equals to KF into what is M, 1000 into WB divided by MB into WA. Okay. Now, so if you want to calculate the molar mass of the solute, how you will calculate? So take this here, this side, and this will go here. So it will be 1000 into KF into WB divided by WA into delta TF. Okay, so this is the formula to calculate the amount molecular weight of the solute. Okay, so this is freezing point depression. So how the freezing point depression can be calculated, okay, by using this particular formula. So the molecular mass of a non-volatile solute can be calculated by using this formula. Please make this a note. Please make a note. So like this, we can calculate the freezing point depression. Okay, so what do you mean by freezing point depression? Here we are seeing how the change in vapor pressure takes place, how the variation takes place when you have a pure solvent and when you have a solution. So the difference, okay, so you can see the vapor pressure of the solution is less as compared to that of the pure solvent. So thus the freezing point of the solution is also lower as compared to the pure solvent. So when you take the difference between these freezing point, that is delta, that is a freezing point of a pure solvent minus the solution, okay, that is your delta TF. So delta TF, you know what is molality. Okay, so we know that delta TF is directly proportional to molality. Molality is nothing but it is a concentration term. So molality is what? So molality is your weight of the solute dissolved in 1000 kg, that is a 1 kg of solvent. So by using this formula, we are substituting in 1 and we can calculate the molecular mass of the non-volatile solute. Is it clear? Yes. Okay, fine. So this is about freezing point, depression, constant. Okay, we'll go for the next one. So we are going to solve the problems at the end. Okay, next is osmotic pressure. Okay, next is what? Osmotic pressure. So osmotic pressure is what? Osmotic pressure is your what? It is a phenomena. Okay, it is a phenomena where there is a flow of solvent molecules into a semi-permeable membrane. Okay, from a pure solvent to a solution or from a dilute solution to concentrated solution. So this is osmotic pressure. Now, if you consider a sugar solution, okay, consider a sugar solution in an inverted funnel. So what you do? So when you have a beaker, okay, you have a beaker. So in this beaker, what I'll take? I'll take, okay, in this funnel, okay, I'll take a sugar solution. So what I'll take in this, I'll take a sugar solution, okay, and you have a solvent here, okay, a pure solvent here. So what you are doing here? So there is a semi-permeable membrane here. Okay, so there is a semi-permeable membrane. So what is the role? What is happening here? Okay, let me explain you. So here what happens? So when we are taking a sugar solution into this inverted funnel, okay, and you have a semi-permeable membrane. Okay, so this is dipped into a pure solvent. So take that pure solvent as water. Okay, so it is observed that what will happen, that the water will flow from the beaker into the funnel. So what will happen, the whatever the water is there, it will flow into the beaker, okay, that is into the funnel, which is which consists of sugar solution. So as a result, what will happen to the level of the sugar solution which is present in the funnel? It will increase, right? Because the solvent molecules, the water molecules starts passing through the semi-permeable membrane into this funnel, which consists of sugar solution. So simultaneously, what will happen? There will be rise in the there will be rise or it increases. Okay, the level of the solution will increase. So what will happen? Similarly, okay, so similarly, if these two solutions of different concentration are separated, so these two solutions, okay, you can see that these two solutions are different. One is a water solvent and another is a sugar solution. Sugar solution is nothing but sugar dissolved in water. Okay, so these are separated by a semi-permeable membrane. So why they are separated? So that the solvent molecule is flowing from a solution of lower concentration to solution of higher concentration as compared to your water and the sugar solution, okay, which is concentrated. The sugar solution is highly concentrated and your water is low concentrated. Okay, so what is happening? You can see that the lower concentration, okay, solution is flowing into the solution of higher concentration. So this flow, okay, this flow of solvent molecules, okay, which are moving from the solvent into the solution, okay, through the semi-permeable membrane. This is called as osmosis. Okay, what is this called as? It is called as osmosis. Understood? Is it clear? So this is osmosis. Or you can say that from a lower concentration, okay, when the phenomena of flow of solution from a dilute solution to the concentrated solution is called as what? It is a through a semi-permeable membrane. Okay, so through a semi-permeable membrane. So this word is important. Okay, so the phenomena in which the flow of solvent molecules from the solvent into the solution, okay, or from the dilute solution into the concentrated solution through this semi-permeable membrane. You can see the semi-permeable membrane which I had drawn here, right? So this is a semi-permeable membrane. So what is happening? The water molecules are flowing and thus there is a rise in the what increase in the level of the solution, sugar solution. So this is called as osmosis. This flow is called as what? This phenomena is called as osmosis. Got it? So this osmosis, so in generally how it is applied, so blood cells, okay, blood cells, they collapse when placed in saline water. So this is one example. So whenever you what is it? You place blood cells, okay, into the saline water, they get collapsed. Then your flowers, okay. Now when the flowers, when they are what you say? When you pluck them from the tree, okay, when you pluck them from the tree and you keep those flowers aside, how they'll become? They'll become dry, like they will lose their moisture. You can see. Then what if you put that stem? Okay, the flower. Suppose the flower. Okay, you are kept aside. Now that same flower with the wing. Okay, if you insert it in a water. Okay, what will happen? Again, the flower will become fresh, right? So it will get revived. Okay, it will get revived. So this is another example of osmotic osmosis. Okay, then this raw mangoes. Okay, raw mangoes also. Raw mangoes. Okay, so when you put them into salt solution, okay, or salt water to make pickles, how they get shrivel, right? Where how they get soaked into that. So this is also a osmosis. So these are the examples of osmosis. Understood? So what is semi-permeable membrane? So semi-permeable membrane, okay, it allows only the solvent molecules. Okay, they always allow the solvent molecules through to pass through it, okay, and not the solute particles. Only the solvent molecules are passed through this semi-permeable membrane. Is it clear what is osmosis? Yes, is it clear? So what are the examples of semi-permeable membrane? Okay, so it can be your cellulose and cellulose acetate. Okay, so it is an artificial semi-permeable membrane, and your natural semi-permeable membranes are animal bladder, then cell membrane. Okay, parchment paper, okay, copper ferrocyanide. So copper ferrocyanide, this is a artificial semi-permeable. What do you mean by artificial? Artificial means man-made. Okay, natural means available naturally. Okay, is it clear what is osmosis? So osmosis, it is a phenomena of flow of solvent molecules, okay, from the solvent into the solution, okay, or from the dilute solution to concentrated solution through semi-permeable membrane. Okay, through semi-permeable membrane. Is it clear? Yes, is it clear? Is osmosis clear? Okay, others? Okay. So next is osmotic pressure. Okay, next is osmotic pressure. So next we are going to, so we have understood now what is osmosis. Now we'll see osmotic pressure. Okay, so the flow of solvent molecules from the solvent into the solution through the semi-permeable membrane. Okay, now you know that you can see the flow. Okay, the solvent molecules, what is happening? The solvent molecules, they are entering into the solution. How they are entering into the solution? They are entering into the solution through the semi permeable membrane. Okay, the solvent molecules, they are entering into the membrane through the semi permeable membrane. So this the entry, okay, now this entry of the solvent molecules into the what is that solution. So this was the semi-permeable membrane, and here was your inverted funnel. Okay, so in which we had taken the solution. So the entry of the solvent molecules into the solution, okay, through the semi-permeable membrane, it can be stopped. How it can be stopped? Okay, so if you put some extra pressure, okay, if sufficient pressure is applied on the solution side. So from this side, if you put some pressure, okay, if you put some pressure from the solution side, what will happen? The movement of solvent molecules into the solutions can be stopped. So this pressure, okay, this pressure which stops the osmosis, okay, is called as osmotic pressure. Is called as what? Osmotic pressure. So what is osmosis? The flow of solvent molecules, okay, into the solution through the semi-permeable membrane is called as osmosis. Okay, so this osmosis can be stopped. How it can be stopped? By putting the pressure, okay, on the semi-permeable membrane in the solution side. Okay, so this is called as osmotic pressure. Okay, so this pressure which stops the osmosis is called as osmotic pressure. Is it clear? So you can see on the solution side, you are putting some extra pressure. External pressure is put so that the solvent molecule cannot move. So osmotic pressure of a solution is equal to the external pressure applied on the higher concentration. Which is higher concentration? The solution side is called as the higher concentration, so that to stop the process of osmosis. So this is called as osmotic pressure. Okay, this is called as osmotic pressure. Is it clear? Yes. So suppose now this osmotic pressure also, okay. So suppose so this is a so you can see this apparatus, right? So you can see that on one side you have a solution, and another side you have what? Another side you have a solvent, right? You can see this diagram. Yes. So you can see here the picture. So here what you can see is, just a second. Okay, so here you can see that here there is a solution. Okay, you can see the apparatus where you have a solution in one and solvent in another. Okay, and they are separated by this membrane. So here is a semi-permeable membrane. So what is happening? The osmotic pressure is applied on the solution side. Okay, so the osmotic pressure of the solution, what is that? The excess pressure, okay, which is applied on the solution so that to prevent the flow of solvent molecules into the solution side. Okay, this is your osmotic pressure. So what is osmotic pressure? So osmotic pressure is also a colligative property. Okay, it comes under the colligative property, right? We know the four important colligative properties. So under that, this is also colligative property. So according to Van 't Hoff, so Van 't Hoff was a scientist. What he observed that for dilute solutions, okay, for dilute solutions, osmotic pressure is directly proportional to concentration. Okay, Van 't Hoff was a scientist. He observed that osmotic pressure is a colligative property, and this colligative property, it is directly proportional to what? It is directly proportional to concentration, which is denoted by C. Okay, concentration of a solution and at a given temperature. At a given temperature. So osmotic pressure, it is denoted by pi. Okay, this is pi. Pi is equals to, so when you remove this proportionality sign, so that is pi is directly proportional to concentration. So when you remove this proportionality sign, you have to introduce a constant. So it is C, R and T. We are introducing the constant, that is gas constant. G is nothing but your gas constant. Okay, so T is at constant temperature. So what is that? The terms, so C is a concentration, okay, in terms of molarity. Okay, so pi is equals to, what is concentration? Concentration is nothing but number of moles, okay, number of moles of component B, okay, upon the volume. That is concentration is number of moles upon the volume, okay, volume of the solution into R T. Okay, so V is here your volume of solution in liter containing number of moles of solute. So concentration is nothing but your what? Concentration is molarity. What is molarity? Molarity is number of solute dissolved in 1 liter of solution. So this is NB by V. Okay. Now what is so here what we are doing? So if we want to calculate the number of that is a weight of the solute. Okay, so if WB, okay, if we are considering WB is what? WB is weight of solute, okay, weight of solute in grams, okay, and MB is what? MB is molar mass, okay, of solute, yeah, that is dissolved in the solution. Then we know that how to calculate the NB, that is number of moles. Number of moles can be calculated as given weight of the solute upon molecular weight of the solute. So this is the formula to calculate the number of moles. So we'll substitute this here in this equation 1. I'll write it as equation 1. So it will be pi is equals to, okay, MB is what? NB is WB divided by MB, okay, and RT, that is VRT. So what we'll do, we have to calculate now. I want to, what we are interested in, we want to know the, that is how to calculate the molecular weight, right? So this will take this side. So MB is equals to, if we shift here, pi will go here. So it will be WBRT divided by pi and V. So this is the formula to calculate the molar mass of a non-volatile solute, okay, can be calculated using this formula. So please note this. Yes, so what is concentration? Osmotic pressure is directly proportional to concentration. Concentration, it is expressed in terms of molarity. What is molarity? Molarity is nothing but number of moles of solute dissolved in 1 liter of solvent. So that is NB divided by V into RT. Okay, so how to calculate the number of moles? Number of moles can be calculated by given weight divided by the molecular weight. So if you substitute this in 1, okay, you will get the formula. So this formula, by using this, we can calculate the molar mass of non-volatile solute. Is it clear? Is this clear about osmotic pressure? So osmotic pressure is very important. Okay. So these are the 4 important colligative properties. Relative lowering of vapor pressure. Then you have elevation in boiling point. Then freezing point depression and osmotic pressure. Okay. Osmosis, osmotic pressure. Is it clear? Okay. So next is, so on the basis of this osmotic pressure, okay, the solutions are divided into 3 types. So that is isotonic, hypertonic, and hypotonic. So these are important, okay, questions asked in exams for 2 marks, like in the terms of definition. What is a hypotonic solution? What is isotonic solution? What is hypertonic solution? With examples. So like this 2-mark question. So very important. You can mark this as important. Okay, so what do you mean by isotonic? So first we'll see, so depending upon the osmotic pressures, okay, so these are, the solution is divided into 3, isotonic, hypertonic, and hypo. What do you mean by isotonic? Solutions having same osmotic pressure. So when the osmotic pressure of the 2 solutions at a given temperature, okay, is same. Osmotic pressure is nothing but the concentration. Okay, if the 2 solutions, if they have same concentration, concentration is nothing but is directly proportional to osmotic pressure. So you have to mention that. So the solutions having same osmotic pressure at a given temperature, so this word should come, are called as isotonic solution. Okay, so for example is important. Please make it a note. Osmotic pressure of a fluid inside the blood cell is equivalent to that of the NaCl solution, that is in the normal saline solution. Okay, so this is an example of isotonic solution. Then, if second is what? If a solution has higher osmotic pressure, if the solution has higher osmotic pressure at given temperature, then the solution is called as what? Hypertonic. Okay, it is called as what? Hypertonic solution. It is called as hypertonic solution. Okay. So on the other hand, if you have lower osmotic pressure, if you have lower osmotic pressure at a given temperature, then it is called as what? Hypotonic. It is called as hypotonic solution. So please make this note. So when you have same osmotic pressure at given temperature, isotonic, then higher osmotic pressure at given temperature, hypertonic, and lower osmotic pressure at given temperature, then it is hypotonic solution. Okay. So what will happen? So if this blood cell, so what we have compared in the isotonic solution, so the molar concentration of the that 0.91% NaCl pure isotonic with human RBC. Okay, so this is the example of isotonic solution. Now these blood cells, okay, if the blood cells, now whatever the blood cells are there, okay, if they are placed in saline water containing more than 0.91% of NaCl solution, then what will happen to the cells? Yes, what will happen? Then the water, okay, then if you put the blood cells into 0.91%, more than 0.91% of NaCl solution, then what will happen? The water will flow out of the cell. The water will flow out of the cell. And what will happen to the cell? The cell will shrink. Okay, the cells will shrink or they will get collapse. So this is in terms of what? This is in terms of your hypotonic solution. And if the concentration of this is this is in terms of hypertonic. Now if the concentration of this what? Salt concentration is less, if it is less than 0.91%, then what will happen? the water will flow into the blood cells. Okay, it will flow into the blood cell, and what will happen to cells? The cell will swell. The cell will start to swell. Swelling takes place. Okay, the swelling will takes place. So this is in terms of your osmotic pressure. So these are the three types, okay, of solution based on the osmotic pressure. So when so if you keep the cells, okay, if you keep the cells in the blood cells in the saline solution more than 0.91%, what will happen? The water will start to flow into the cell and the cell will shrink, or it is called as what? Cell will start to collapse. Okay, in the hypertonic. In hypotonic, what will happen? If the concentration of the NaCl is less than 0.91%, okay, then the water will flow out. Okay, the water will flow into the cell. Okay, and then what will happen? The cell will swell. Okay, the swelling will takes place. If in okay, if your legs are having swelling, what they say that the water is accumulated more in your legs, like that. So the swelling takes place. If the water goes inside the blood cells, swelling takes place. And if the water goes outside the body, then it starts to shrink or it starts to collapse. Okay, so here the concentration of NaCl solution is less than 0.91%, and here if it is more than 91%, then it will go out of the cell. Understood? Understood these three definitions of hypertonic, hypotonic, and your isotonic solution. Is it clear? Okay. Next, we are going to discuss something called as reverse osmosis. Okay. Now we know what is osmosis. We know what is osmotic pressure. Now there is something called as reverse osmosis. Okay. So what is reverse osmosis? So the process of flow. Okay. If I take I'll draw it here. Okay. Okay. So this is what? This is your semi-permeable membrane. Okay, in this you have salt water. In this chamber you have salt water, and in this chamber you have fresh water. You have what? Fresh water. Okay. Now what is happening? Now you are in the solution side. So this is the solution side. Solution side, what you will do? You will apply pressure. Okay, so pressure. So here you can apply pressure. So this is the pressure point. Okay, now what is happening? The process. So the process of flow of this solvent molecule. So in this, what is there? Your fresh water. Fresh water is your pure solvent, right? This is your pure solvent, and this is your salt water is the solution. So the process. So what is osmosis? The flow of the solvent molecules into the solution, okay, through the semi-permeable membrane is called as the osmosis. So the process of flow of this solvent molecules, okay, from the solution into the solvent. Now, if the process, what is reverse now? Now, what is reverse osmosis? Reverse osmosis means what? The phenomena is occurring reversely. Means the salt molecules, the process of flow of solvent molecules from the solution into the solvent. So what is happening? from the solution part, the solvent molecules, the solution, these are moving into the solvent through the semi-permeable membrane. Okay, the flow of solvent molecules from the solution into the solvent through the semi-permeable membrane by applying a external pressure. So when you put a external pressure, okay, what is happening? The pressure on the solution side will be greater than the osmotic pressure. So this is called as reverse osmosis. Okay. So example, so very important definition. What is reverse osmosis? And ask for 2 marks. Important, very important. What is reverse osmosis? So you can write it down. The process of flow of solvent molecules from the solution into the solvent through the semi-permeable membrane by applying external pressure. So you know that when you put external pressure on the solution side, the process will be reversed. Okay. So the molecules of the solvent molecules from the solution will start to move into the solvent, that is into the pure solvent. So this is your reverse osmosis. So what is the example? So it is, example is desalination. Okay, desalination of seawater. Okay, desalination of seawater. So whatever the pressure is required, okay, for reverse osmosis, it is quite high. Okay, it is very high. So whatever for reverse osmosis, the pressure which is applied, it is very high. And which semi-permeable membrane is used? It is cellulose acetate. Okay, cellulose acetate, this is used. What? Semi-permeable membrane is used. Okay, and so this semi-permeable membrane, what it will do? It will allow only the passage of solvent molecules and not the passage of solute particles. Okay, solute molecules. So only the water can flow. Only the water can flow and not the impurities or any ions which is present. So for seawater also. So what is done? So what is done? So if you take salt water here, right? So in that salt water, if I replace this salt water with sea water, so what is done? The water molecules will flow from the semi-permeable membrane, okay, and it will move in this fresh water chamber, okay, because you're putting pressure more. You're putting pressure more on the solution side. So only the water molecules will be passed through the semi-permeable membrane and not the impurities or any ions which are present in the sea water. So by this you can do the desalination of seawater. You will get a pure water. So reverse osmosis, it can be used in purification. Okay, you can get pure water by this process. Okay, by taking seawater, you can get the pure water. Okay, so understood what is reverse osmosis? Is it clear what is reverse osmosis? Yes, okay. So you can see this is hypertonic. Okay. So in hypertonic, what is happening? The concentration, okay, of the NaCl, okay, is quite high. So what is happening? The blood cells are moving out of the, the water molecules are moving out of the blood cells, right? So this is hypertonic. Isotonic, the osmotic pressure is equal, okay, of both the solution, that is NaCl, that is 0.91, it is equivalent to that of the RBCs. Okay, so it is the osmotic pressure or the concentrations are same of both the cells. So it is isotonic. Hypotonic means what? What will happen if the blood cells, okay, if they are placed in the NaCl solution, which is less than 0.91 concentration, what will happen? The water will flow into that. So water will flow into the RBCs and you will result into what will happen? The cell will start to swell. Okay. So this is hypotonic. So this is how it is explained. Okay. So next we are going to discuss about abnormal molar mass. Okay. Next we are going to discuss about abnormal molar mass. Okay. So we know now what are colligative properties. We have studied the different colligative properties. So on the basis of colligative properties, what we can calculate the molecular mass? Yes, we have seen now. So we have seen 4 different colligative properties. So based on that, we can calculate the molecular mass of the solute. Okay. So how, so on the basis of this colligative properties, what we can do, we can get the, what is that? We can get the molecular weight of the solute. Okay. And there are conditions. Okay. There are few conditions which should be satisfied. So first is that the solution should be dilute. Okay. The first condition is that the solution, whatever the solution you are taking, it should be a dilute solution. Okay. Then second condition is that the solute particle, whatever the solute particles are there, it should not undergo dissociation or association in the solution. Okay. It should not go dissociation or association in the solution. Dissociation means what? Suppose NaCl should not split into Na plus and Cl minus. This is dissociation. Association means what? They get associated to give you NaCl like this. So this is association. Okay. And this is dissociation. So the solute particles, whatever the solute particles you are taking, they should not undergo dissociation or association in the solution. If suppose there is any association or dissociation of the solute particles, then the number of solute particles in the solution will change. So if any association or dissociation takes place in the solution, what will happen? We know that what is colligative property? It depends upon the number of number of solute particles. So if in the solution, if there any association or dissociation takes place, then the number of solute particles will change. Okay, it will change, and thus what will happen? The value of colligative property also changes, right? So this all depends. You know that colligative property depends on number of solute particles. If in the solution any association or dissociation occurs, then what will happen? Number of solute particles will change. As a result, colligative property also changes. Okay. So thus the molar mass. So whenever we are discussing about molar mass, it should be determined. How it will be determined? It will be determined on the basis of colligative property. Okay. Either it is lower or higher than the normal value. So if the molar mass has to be determined on the basis of any colligative property, if it is either higher or it is normal, then it is called as abnormal molar mass. Okay. So if you get the molar mass, if you calculate the molar mass, and this molar mass, if it is higher or if it is lower, okay, as compared to the normal value, then this is called as abnormal molar mass. Okay, so it is called as abnormal molar mass. So abnormal molar mass, okay, if you have a if you have dissociation, okay, so abnormal molar mass, if the solution undergoes dissociation, so what will happen? The ionic compounds. Now you have some ionic compounds like KCl and all. So what will happen when you add this KCl into water? Okay, if you add it into water, what it will do? It will dissociate. It will dissociate into K plus and Cl minus ions. Okay. So for every 1 mole of KCl, there will be 2 moles of particles. You can see 2 moles of particles. Okay. So those colligative properties will become double. You can see in dissociation. Okay. If I consider abnormal molar mass in dissociation, if I consider 1 mole of KCl, okay, 1 mole of KCl, and if I dissolve it in water, so how the dissociation will take place? KCl will split into K plus and Cl minus. Okay, so you get 1 mole of K plus ions, 1 mole of Cl minus. So 1 mole of KCl will dissociate to give you 2 moles of particles, right? To get to 2 moles of particles. So the colligative property, what is happening to colligative property? When it is undergoing dissociation, it will get double. Okay, it will get double than the theoretical value. If you have only KCl, if the solute particle was only present in the solution, what would be the value? Colligative property, as it depends on number of solute particles, it would be only 1. Okay, because it is not under, if it was not undergoing any dissociation. But when this solute particle KCl is undergoing dissociation, what is happening? What is happening? It splits into 2 moles of particles. Okay, you can see KCl, it splits into K plus ion and Cl minus ion. So you results into 2 moles of particles. Okay, so whatever the theoretical value is there, okay, you can see that observed value is double than the theoretical value. So theoretical value is what? Theoretical value is 1 and observed value is 2. Right? Theoretically, only 1 could be present and observed it is 2. So this is the abnormal molar mass for dissociation. Now, if we consider association, okay, if we consider now association, so again, so some of the solute particles, they will undergo association if you add or if you dissolve it into the solvent. Suppose I take acetic acid. Suppose I take acetic acid. So this acetic acid, so if I take 2 moles of acetic acid, it will get associated into CH3, COO, H.
ಯಾರು ಎಲ್ಲಾರ್ಕಿಂತ ಚಂದಾಗ ಅಗ್ದಿರ್ತಾರಲ್ಲ ಅವ್ರನ್ನ ನನ್ ಮಕ್ಕಳಕ್ಕ ಕೊಡಿಲ್ಲ ಅಂತ ಹೇಳಿಸ್ತಾರಲ್ಲ ಬಾಯಿಗಳನ್ನ ನಾನು ಎಲ್ಲಿಗೂ ಬರಲ್ಲ ಸ್ವಾಮಿ, ನಾನು ಎಲ್ಲಿಗೂ ಬರಲ್ಲ.
Okay. So what is happening in association? So this acetic acid molecules, okay, it will get dimers. Okay, if I take, if it is dissolved in a solvent like benzene, okay, so due to hydrogen bonding, it will form CH3. So if I consider acetic acid, CH3COOH, okay, you get CH3COOH twice. So that is, it is undergoing dimerism in what is that? Benzene, okay, due to hydrogen bonding. And so for every 2 moles, so what you can see, for every 2 moles of acetic acid, okay, there will be only 1 mole of particle. Okay, so what you can see, the observed colligative property will become half. Okay, so observed is half as compared to that of theoretical value. So whenever it is undergoing dissociation, it will be doubled, and whenever it is undergoing association, it will be what? It will be half. Okay, so this is the abnormal molar mass. So abnormal molar mass is given by something called as Van 't Hoff factor. Okay, so to calculate the extent of dissociation or association, so Van 't Hoff factor is introduced, and this Van 't Hoff factor is given as I. You can see here, I is equals to normal molar mass. Normal means theoretical. Okay, theoretical, and abnormal means what is absorbed. Okay, what is observed. Okay, so I is equals to observed colligative property upon calculated colligative property. So I can also be given as total number of moles of particles after dissociation or association upon number of moles of particles before dissociation or association. So this is the formula. So in case of association, what will happen? I will be always less than unity. It is I is less than 1. And in case of dissociation, I will be greater than 1. So these things you have to keep in mind. Is it clear? So for any solid particles which is undergoing association or dissociation, the colligative properties are modified. Okay. So it is modified, and the modification, I'll give the modification. So if it is undergoing any abnormal molar mass, okay, so it will be modified with that values. Understood? Is it clear? So what is abnormal molar mass? So as you know, abnormal molar mass, okay, it depends on what? Abnormal molar mass, it okay, if the value of molar mass is either higher or lower as compared to the expected or normal value, then it is abnormal molar mass. So if the if it is undergoing dissociation, the value will be doubled, and if it is undergoing association, the value is half. So as you know, colligative property, it depends on the number of particles. Okay, so in the solution, the solute particle should not undergo any association or dissociation. If it undergoes association and dissociation, then the number of solute particle changes. As a result, the number of colligative property also changes. Okay, so colligative property also, the value of colligative property also changes. So so you remember this, that is, when you have association, the value of I is less than 1, and when you have dissociation, the value of I is greater than 1. Is it clear? Yes. So we'll see one problem now. Quickly. So is it clear up to here? Any doubts? Yes, any doubts, students? So this was all the theoretical part, okay, of the solution chapter. So after this, we are going to discuss the problems. Okay, so whatever we have seen. So concentration terms, we have discussed one problems. Okay. Now next I have to take one problem on Henry's law and one on Raoult's law. So that also I'll take. So so as we have completed colligative properties, so first I have taken one examples on each colligative property. Okay, so first one, so see, 5.8 grams of non-volatile solute was dissolved in 100 grams of carbon disulfide. Okay, disulfide, that is carbon disulfide is CS2. The vapor pressure of the solution was found to be 190 mm of Hg. Calculate the molar mass of the solute given the vapor pressure of the pure solvent, that is CS2, is 195 mm of Hg. What is the molar mass of CS2? So molar mass of CS2 is given as 76 gram per mole. Now what all are the given things? So we have to calculate here what? This is a problem based on what? Relative lowering of vapor pressure. Okay, so based on relative lowering of vapor pressure, so first I'll write the formula. So the formula is P1 naught minus P1 divided by P1 naught is equals to W2 into M1 upon the M2 into W1, right? If you have the formula, see, check. So this is a formula which we are going to use. Now, what are the things which are given? So 5.8 is the weight of the solute. Okay, that is 5.8 grams. What it was a non-volatile solute dissolved in 100 grams of carbon disulfide. So that is a weight of the solvent, 100 grams. Then the vapor pressure of the solution is P1. Okay, is given as 190 mm of Hg. Okay, and calculate the molar mass of solute. So calculate the molar mass of solute is M2. Okay, then given the vapor pressure of pure solvent. So pure is given, that is P1 naught is equals to 195 mm of Hg. And we have to calculate the molar mass of molar mass of the solvent. Molar mass of the solvent is what? Molar mass of the solvent is given here, 76 gram per mole. Okay, now put all these things. So P1 naught is 195 minus P1 is 190 divided by P195 equals to what is W2? W2 is 5.8 into what is M1? M1 is 76. Then M2 is don't know. We don't know M2. We have to calculate. W1 is 100. Okay. So now do this simple calculation. I hope you have calculators now. Yes. So do the simple calculation. So first you do 195. 195 minus 190. Okay, is 5 divided by 195. So 5 divided by 195 is, you will get this as 0.0256 equals to, okay, equals to 5.8 into 76. Or what you can do is, first I will shift this here. Okay, first I will calculate. First I will shift it here. That will be better, I guess. Okay. See here, first I'll shift it, then we'll calculate. Just a second, because our unknown should be on the left hand side. So this I have to shift. Okay, first I'll shift that. Wait. So let me take another color. Yes, here. So M2. So I'll take M2 here. So if I take M2 here, 195 minus 90 is, here I'll consider it as 5. Okay, I'll take it as 5. This is 5. So M2 is equals to, this will be here 5.8 into 76. This 195 will go to numerator. So this will become 195. Okay. And here this will go denominator. So 100 into 5. Now you can do. Now it will be easy for you. Okay. So M2 will be equal to, so 5.8 into 76 into 195 you do first. So you'll get it as 85 956. Okay. Divided by 100 into 5 is 500. So do this now calculation. 85 56 divided by 500. So you get 171.9. Okay. And the what will be the unit? It is gram per mole. Is it? Yes. So molar mass is given as gram per mole. Everybody got this? 172. Okay. Gram per mole. Yes. Sri Varuni has answered it right. Others? Others are solving or no? Okay. Is it clear? Understood? So this is a formula for calculating the relative lowering of vapor pressure. Okay. Is it clear? Yes. Any doubts? So rest of the problems we are going to discuss in the next class. Okay. So any doubts in today's session, students? Any doubts? So this was a problem based on relative lowering of vapor pressure. So it is a 3 marks question. Okay, important, compulsory asked from this section. Okay, qualitative property, any one of the qualitative property, it will be asked. Okay, for 3 marks. So how the marks is divided? 1 mark for the formula, 1 mark for the substitution, and 1 mark for the answer with the correct unit. Unit is very important. Okay. I hope everyone has understood the today's session. Okay. So tomorrow, one more day, we are going to see the remaining problems. Okay. So this, so whatever the theoretical part is there, okay, of this chapter solution, so that we have completed. So one more day, we will solve the problems. Okay. Fine. So I hope everything is clear. So if you have any doubts, please ask them in the next session. Okay, please note it down and you can get it in the next session. So thank you, dear students. Yes, okay, fine. So I shall end the session here. Okay, we'll be meeting in the next class. Thank you.